So welcome again to this lecture number 4 of the course on solar photovoltaics, principles, technologies and materials. So we'll just do a brief recap of last lecture. So in the previous lecture we learnt about what is solar constant, basically how much is the energy which is received on the outer surface of atmosphere, and then we looked at what are the atmospheric effects which affect the intensity that you receive on earth on the horizontal plane, and then we also looked at the concepts related to direct, diffuse and global radiation. So direct radiation is the one which directly is in line with the sun with respect to the object, there is no deviation. Diffuse is the one which comes from the surroundings, and global is the sum of these two. And then finally we also looked at air mass index, which is essentially a measure of how much absorption the sun ray has gone into depending upon its angle. So you can have sun ray coming at from zenith directly from top. It can come from horizontal direction because the sun moves from east to west, and so when it is at east, it's nearly parallel to the earth, and as it goes to the zenith, it's vertical and the beam comes directly onto the earth, and then it goes to the west. So because there is an angular variation of sun's position with respect to earth, there is the amount of absorption that the beam goes through the atmosphere also changes because the path length is different. As a result, we need to standardize this, and the standard has come about to be AM 1.5, which corresponds to an angle of about 48.2 degrees, which basically averages out the overall rotation of sun throughout the course of the day with respect to the let us say solar panel. So this is what we take during measurements as well. So generally when you make measurements of solar panels, the value is taken as AM 1.5 G, and this is what it basically means. So it's basically 100 milliwatts per centimeter square coming onto a surface, which is sum of direct and global diffuse radiation. G means global, 1.5 means corresponding to the average angle of 48.2 degree, which is the average intensity of the sunlight that should fall on a surface at a given time. Now what we will do in this lecture is we will look at aspects related to sun and the geometrical aspects of sun and earth. First we will just look at the expression of intensity as a function of air mass. So the intensity of the direct component of sunlight, so this is basically with respect to the sunlight throughout the day is given as ID is 1367, which is a solar constant, multiplied by 0.7 to the power AM to the power 0.678. So this is an empirical equation, and this 0.7 is because of the fact that about 70% of the radiation reaches the earth, 30% is lost. So this is the 0.7 factor. This is really after atmospheric so you can see that if this factor was equal to 1, then this would be about 1367 into 0.7. So whereas the 0.678 is the empirical fit to the data. So let me give you certain values now based on this. So if you look at the intensity range, let us say theta z value is varying here, and let us say we take certain times of the day AM, and energy range which is observed and energy as per formula. So if you look at the angle of, for example, if you look at AM0, AM0 is 1367 and the value is also about 1353 or so, okay. And if you look at 0 degree of theta, then this AM is equal to 1, and this the value which is observed is about 840 to 1130, which is about 990 plus minus 15%, whereas the calculated value is about 1040. This is all watt per meter square, okay, watt per meter square. And if you look at a value of, for example, let's say 30 degree gives you about 1.15 AM value, and this gives you a range of 780 to 1100, which is equivalent to 940 plus minus 17%, and the value that you calculate from formula is about 1010 watt per meter square. If you look at AM 1.5, which is 48.2 degree, so this is AM 1.5, we have a variation of 870 plus minus 21%. So this is energy range basically observed, which is because of pollution, so you have this much of variation, and the formula predicts a value of about 930 watts per meter square. And if you go to higher angles, let's say about 75 degree gives you 3.8, and this gives you a value which is 560 plus minus 41%, and this is about 470. And if you look at 90 degrees, this is 38, and 98 is, you cannot estimate the, so let's say about 85 degrees, okay. 90 degrees parallel to horizontal, which means nothing is coming onto the panel. So we look at 85 degrees, that is more realistic. 85 degrees give you a value of about 10, and this is a value which is 280 plus minus 70 degrees, 70%, and the value that you get is about 270. So you can see that the variation also increases as the angle increases, okay, because the sun ray has to travel a longer length as compared to the values which are coming directly onto the normal. So when the path length increases, the unpredictability in the values also increases. So you can see the error, 15% at 0 degree, 17% at 30 degree, 21% at 48.2 degree, and this progressively increases to about 70% at about 85 degrees. So when the path length of sun increases through the atmosphere, the error, the unpredictability in the values also increase, because the atmospheric effects become more and more stronger. So smaller the atmospheric effects are, better is the predictability of radiation. Now we are going to look at the geometrical relationships. So first and foremost, we are all aware of, if this is our Earth, let's say, okay, so somewhere here you have North Pole, somewhere here we have South Pole, and these great circles so the ones which are parallel to the vertical axis, or these are basically great circles of equal diameter looked at various angles with respect to the north-south axis. These are called as great circles, and they depict what we call as longitude, okay, and longitude is measured with respect to Greenwich. So Greenwich is taken as, so generally we depict it as, so with respect to Greenwich, which is in England, okay. So for England the longitude would be to start with 0, and then we measure the other locations longitude with respect to it. So this is longitude, and the circles which run horizontally, they are called as, so at the center the biggest circle, this would be the equator, right, and the ones which are running parallelly, these are called as small circles, okay, and these are called as latitude circles, okay, and these LATTI. So these go, so this way it will be positive, and this way it would be, so this would be 0 degree latitude. On top of it, you are in the you are closer to North Pole, and as you go in the bottom half, it will be in the south, closer to South Pole. So this is basically is the northern hemisphere, and this would be your southern hemisphere. So Australia, for instance, would fall in some southern hemisphere. The South America would, most of it would fall in southern hemisphere, whereas and some part of Africa would also fall in southern hemisphere, whereas India and China and Russia and most of the Europe, all of the Europe and some part of Africa will fall above the equator. That will be in the northern hemisphere. So the relations of angles change depending upon whether you are in northern hemisphere or southern hemisphere. Most of the calculations that we will do in this lecture are related to northern hemisphere, but there are some pluses or minuses which come into picture when you deal with the northern hemisphere, southern hemisphere. So generally this longitude is determined as is depicted as lambda, and latitude is depicted as phi. So based on, now we also know that the earth is so since we measure our time with respect to the Greenwich Mean Time, which is located in England, so Greenwich is so our time is 5:30 hours ahead of Greenwich Mean Time, whereas America would be some hours behind Greenwich Mean Time, because the earth is rotating around its axis. So the sun rises first in, let's say, Australia or closer to Australia in the far east, and then it comes to eastern nations, and then sunlight comes to India, Pakistan, and then goes to Europe, and then goes to, but the reference is taken with respect to Greenwich Mean Time. So India is 5:30 hours ahead of Greenwich Mean Time. However, the time that we denote as noon doesn't necessarily mean that it is a solar noon. Solar noon means the sun should be on top, that is the solar noon, whereas according to our clocks the noon may be different, and this is because of and these changes happen because of eccentricity in Earth's orbit and various time zones and daylight saving notations that we have created, and so on and so forth. So when we make calculations of intensity, or when we make time calculations, we have to be a little bit more accurate than what we see in the watches. So that is why we need to have a distinction between what we call as local solar time, which is called as LST, and local time, which is called as LT. So local solar time basically implies basically 12 at noon, when sun is highest in sky. So as per sun's position, that should be 12, but local time is not same as LST. So LT is not same as LST. So what it means is that depending upon the time of the year, we can see sun on the zenith, let's say at 1 o'clock, which is actually 12 according to solar time, whereas in our watches at that time we will have 12. So there is a difference of 1 hour. The sun reaches, according to our watches, sun doesn't reach on the zenith at 1 p.m. At 12 p.m. rather it reaches on the zenith at 1 p.m. or maybe at 11:50 p.m. Okay, so there is a difference between the local solar time, which means when the sun is at zenith, and the time in our watches. So we need to have some corrections for that, and these corrections are because of eccentricity of Earth, and then we have time zones, daylight saving. There are some nations which have daylight saving. For example, India doesn't have daylight saving, but many Western nations follow this daylight saving, especially in countries where day and night times vary significantly as a function of time, as a function of time of the year. So to save the daylight, they move their clocks by 1 hour ahead or behind, depending upon time of the year. So for this, we need to make certain calculations. So let's say this is the Earth. Okay, and this is, let's say, the axis of rotation of Earth, and on this we have some position marked as prime meridian, which means lambda is equal to 0 degree, which is called as Greenwich Mean Time or GMT. Okay, and the other one, let's say, is certain other location. This is the local standard time meridian, which is called as LSTM. Okay, so local standard time meridian at the local place, local standard LSTM is essentially 15 degrees multiplied by delta T GMT. So the time difference with respect to GMT is in hours, is equal to, basically you can say, local time minus GMT time. Okay, so if it is 5 p.m. in India, in England it is 11:30 a.m. So the difference of there is 5:30, 5 hours 30 minutes, or you can say 5.5 hours. All right, and 15 degrees comes from the fact that Earth rotates 360 degrees in 24 hours. So every hour it will rotate by 15 degrees. Okay, so this is essentially nothing but 360 divided by 24. Okay, so this is 360 degrees 24 hour. So this is called as LSTM, that is local standard time meridian, and basically we are calculating this in degrees, angular values. And then there is something called as equation of time. Equation time, which is called as EOT in minutes. This is given as, it's an empirical equation to correct for the eccentricity of Earth's orbit and axial tilt of the Earth. Okay, so to correct for an axial tilt, and EOT is defined as 9.87 sine of sum 2b minus 7.53 cos b minus of 1.5 sine b, where b is 360 divided by 365 into n minus 81, okay, where n is the number of day starting from 1st Jan, okay. So 1st Jan would mean n is equal to 1, okay. So this shows a variation which is, you can plot it, and I won't be able to plot it very accurately, but let's say if you plot it as a function of n, and this is EOT in minutes, this is 0. So at certain values it would be, so let's say this is minus 15, somewhere here you have plus 20. So let me mark certain values: 50, 100, 150, 200, 250, 300, 350, somewhere here we will have 365, okay. So the way it will vary is, it will go something like that. So this is 50, 100, 150, and this is 365, okay. So it will go as something like that, and then it will go to certain values between this, and then about 200 it will show a minima, then again at 300 it will show sort of a maxima, and then come to certain, so exact values you can calculate by putting in the formula, but this is the variation it will show. For certain times of the year the equation of time will run into negative, and for certain times of the year the equation of time correction will be in the, will have positive values, okay. So it depends upon the so time correction in minutes, which is called as TC, is given as, so because of longitude variations and for a given time zone we need to correct the time with respect to the local time, okay. So time correction is given as, so TC is given as 4 into longitude minus LSTM, which is what we looked at first, plus EOT, and this factor of 4 comes because you have 15 degrees per hour. So basically every 4 minutes you will have 1 degree, okay. So 1 degree for every 4 minutes, okay, rotation. So let's say you want to look at some, so let's say you want to look at some value. So let's say if I do for Kanpur, okay, since we are in Kanpur, let's say we have a latitude of Kanpur has a latitude of 26.04 degrees and longitude of 80.65 degrees. So let's say we take n is equal to 100, so 100th day of the year, which will probably fall into April, and for this first we need to work out what is the equation of time correction, which we can get from this formula. So we first calculate B by substituting the value of n, and then we apply this in the formula that is above. So if I do it for Kanpur, I get EOT of about -2 minutes, okay, about -2. So time correction is 4 multiplied by 80.65 minus, we said LSTM. LSTM is 15 multiplied by delta T GMT, which is 5.50, right. This is delta T GMT. The difference of Kanpur with respect to delta T GMT is 5 hours 30 minutes. Now that is the whole India, right, but it doesn't, I mean it won't be same for whole India, right, because 5.5 hours 30 minutes is average for India. But if you go to, for example, Rajasthan is further west as compared to Manipur, okay. So sun obviously will rise first in Arunachal Pradesh or Manipur than in Rajasthan. Similarly, sun would set later in Rajasthan than it would set in Arunachal Pradesh. So because of these variations and local variations in longitude and longitude values, you need to correct the time. So and this is equal to, and then we have what we have there. So this is time correction 4 multiplied by longitude minus LSTM plus EOT, and EOT we have worked out as -2. So this will go as -2. So if you do the math, so this is 4 into 80.65 minus 82.5 minus 2, and this will work out to minus 9.4 minutes. So essentially the time correction on 100th day of the year is minus 9.4 minutes. So which means that your solar noon is actually at something like 11:50 AM instead of 12 PM. Okay, so this is the time correction that you need to take into account, and so you can write this local solar time is equal to basically LT plus time correction divided by 60. So this is local time, this is time correction. So this would be in hours, okay, because you are dividing it by 60, okay. So this is how you do the calculation of local solar time with respect to position at which solar panel is kept. So this is what we have done so far. We have looked at this first geometrical relationship, the effect of basically time zone. We haven't yet gone into geometrical relationships, which we will cover in the next lecture. Okay, thank you.